Hi guys, in the last lecture we started with the concept of load flow analysis. There we saw what is meant by load flow analysis, what were the objectives and assumptions of the load flow analysis. Then we analyzed the real and the reactive power injected at each bus. So we found out SI conjugate, which was Pi minus JQi, which came out to be J is equal to 1 to N mod Vi mod Vj mod Yij angle delta j minus delta I plus theta ij. This was the complex power injected at bus number I. Then we computed the Gauss's method to determine the bus voltages. So Vik plus 1 was equal to 1 by Yii Pi minus Jqi Vi conjugate k minus summation j is equal to 1 to n, j is not equal to I, Yij Vj. And based on that we saw two algorithms, one with the PV buses, other without PV buses. We also saw the classification of buses, that is PV bus, PQ bus and the slack bus. And we saw that whenever a PV bus violates the reactive power limits, then we convert it to a PQ bus. In this lecture, we will focus our attention on the next method for the load flow analysis, the more popular one, that is your Newton-Raphson method. So first let us look at a Gauss-Seidel method. Up to now we saw the Gauss method, in which we were doing is Vi k plus 1 was function of V1 k, V2 k up to Vn k. But if we are finding the voltage sequentially, then when I am determining Vi k plus 1, I will already be knowing V1 k plus 1, V2 k plus 1 up to Vi minus 1 k plus 1. These voltages would already have been calculated. So for a faster convergence, rather we will use these voltages to determine Vi k plus 1. That is what I will write is Vi k plus 1 is function of V1 k plus 1, V2 k plus 1, Vi minus 1 k plus 1, then Vi k up to Vn k. So whatever new voltage you calculate, just substitute in the expression. That is, like in the last lecture we solved an example, whenever we are determining V3, we will use the latest value of V2. That way we will achieve a faster convergence. So what will be the equation for voltage exactly? In the Gauss-Seidel method, Vi k plus 1 will be given as 1 by Yii Pi minus Jqi upon Vi k conjugate minus summation j is equal to 1 to I minus 1 Yij Vj minus j is equal to I plus 1 up to n Yij Vj. But this will be k plus 1th iteration, this will be kth values. Okay. And even to further accelerate the convergence, we use acceleration factor. That is given as alpha. Now this acceleration factor is Vi k plus 1 acceleration is actually Vi k plus alpha Vi k plus 1 minus Vi k. Okay. That is your acceleration factor. This alpha belongs to 1.3 to 1.6. This will still improve the convergence because we want that we must get the result in the minimum number of iteration. So that is your Gauss-Seidel method. It is an improvement over the Gauss's method. Next, let us come to Newton-Raphson method. Now Newton-Raphson method is based on the derivatives or the gradients. Hence it is also called as gradient method and it takes the least number of iteration. Okay, but the problem is each iteration is a bit more complicated. That is, time per iteration increases, though the number of iteration reduces, but the time per iteration increases. And here we have to solve non-linear algebraic equation in case of Newton-Raphson method. Now let me illustrate what is meant by Newton-Raphson method. Suppose we have two equations in two variables, something like this. These equations may be linear, may be non-linear. Okay. If these are linear, then they can be directly solved, but the problem comes when the both equations are non-linear. Now we will take an initial guess at these values. Let me say x10, x20. We will check if f of x10, x20 is equal to f1 and f2 of x10, x20 is f2. If such a condition is satisfied, then my solution will become x10 and x20. If not, then what we do is we will introduce some correction, that is x11 will be x10 plus delta x1 and x21 will be x20 plus delta x2. Now f1 of x10 plus delta x1 by Taylor series can be written as f1 x10 plus del f1 by del x1 delta x1 plus higher order terms. Similarly, plus second term will also be there, delta x2, because here this will be a function of x2 plus delta x2 also. Okay. Similarly, f2 will be x10 plus delta x1, x20 plus delta x2. So by Taylor series, this will become f2 x10 x20 plus this will become x20 x10 plus this will become del f2 by del x1 delta x1 del f2 by del x2 delta x2 and higher order terms. So we will consider only up to the first order derivative and neglect all the higher order terms. How are we neglecting higher order terms? We are neglecting based on the assumption that delta x1 and delta x2 are very small. So now what I can write is equal to f1 x10 x20 f2 x10 x20 plus del f1 by del x1 del f1 by del x2 del f2 by del x1 del f2 by del x2 delta x1 delta x2. This is called as your initial guess. Okay. Now this must be equal to f1 and f2 if x1 plus delta x1 is to be a solution. But I'll say 0 0 0 0, that is x10 x20. This will be plus del f1, sorry, not plus, del f1 by del x2 del f2 by del x1 del f2 by del x2. Okay. So now this is called as your Jacobian matrix. And this vector delta x1 and delta x2 is called as your correction vector. Okay. and these are my calculated value. This is my supposed value, which it must be equal, and this is correction vector. Okay. So actually our aim is to determine the correction vector, and how can we determine that? By taking the inverse of the Jacobian. Okay, because initially I will assume the voltage, magnitude and the angles at each bus, and then I will modify those to arrive at the solution. So we need to know what is the modification required in each variable. Now if we interpolate it, cut the slide where I change. Now if we represent it for n variables, how can we represent Jacobian as well as our solution? It will be, that is my supposed value minus calculated value. Supposed value minus calculated value. Supposed minus calculated. This will be equal to Jacobian del f1 by del x1, del f1 by del x2, del f1 by del xn, del f2 by del x1, del f2 by del x2, del f2 by del xn, then del fn by del x1, del fn by del x2, del fn by del xn, and the correction vector will be delta x1, delta x2 up to delta xn. Now when we apply this method to the power flow problem, then the variables or the correction vector will consist of voltage magnitude and the voltage angle, because we wish to determine the solution of the system in which we wish to determine mod V and delta. So let us see how we apply the Newton-Raphson to the power flow solution. Now Pi is actually a function of mod V and delta, and Qi is also a function of mod Vi and delta I. Okay. So what we will do is, correction vector will be given as delta delta or delta mod V. Jacobian will be given as del P by del delta, del P by del mod V, del Q by del delta, del Q by del mod V. This will be the Jacobian of the system. And your mismatch vector will be P supposed minus calculated, Q supposed minus Q calculated. It actually indicates error, or it is called as mismatch vector. Mismatch means what is the difference between the supposed value and the calculated value. Now if we wish to determine the calculated value, this is also represented as J1, J2, J3, J4, just for shorthand. Now if we wish to determine the correction vector, what we will do is, we will take the inverse of Jacobian. So that means P supposed minus P calculated, Q supposed minus Q calculated into J1, J2, J3, J4 inverse is equal to actually delta delta and delta mod V. So that way we obtain what should be the change in the value of delta and the mod V, and then we will update the values of delta and mod V for the new values. As we keep on updating, we will go closer and closer to the actual result. Now let me take a system where I have n buses, out of which one will be slack bus. I am assuming m are the number of PV buses. Then what is the number of PQ buses? N minus m minus 1 will be PQ bus. Remember, slack bus is also a generator bus. So if you are given 10 generator bus, you will extract one slack bus, then 9 will be treated as PV buses. Now, in PQ bus, we need to update to the value of mod V as well as delta. But in PV bus, we need to update only delta. So delta delta will have the unit of how much? Delta delta will be n minus 1 because we want to update it for n minus 1. And delta mod V, that will be n minus m minus 1 because we do not wish to update for the PV buses. Now Jacobian J1 is actually del P by del delta. Now P is known for all the buses, okay, because PV and PQ would know the P. So it is known for n minus 1 bus. Delta delta is to be updated for n minus 1 bus. So order is n minus 1 cross n minus 1. J2 is del P by del mod V. Now P is known for n minus 1 buses and mod V we need to calculate for n minus m minus 1 buses. Now J3 del Q by del delta. Q is known for only n minus m minus 1 buses. Delta is known for n minus 1 buses. Del Q by del mod V. Q is only known for n minus m minus 1 buses and we wish to calculate mod V for n minus m minus 1 buses. So from here we can see J1 and J4 are square matrices. Okay, and what is the order of Jacobian? Here J1 has n minus 1 rows, n minus 1 column. J2 has n minus 1 rows and n minus m minus 1. This has n minus m minus 1 and n minus 1 column, n minus m minus 1 cross n minus m minus 1. So what is total number of rows? N minus 1 plus n minus m minus 1, that is 2n minus m minus 2. What is the total number of column? N minus 1 plus n minus m minus 1. So this is the order of Jacobian, that is 2n minus m minus 2 cross 2n minus m minus 2. The easier way to remember this is, instead of just remembering the formula, we need delta for mod V for PV buses and mod V and mod delta for PQ buses. So that means we will need two equations for PQ bus and one for PV bus. So this is the order of Jacobian. Okay, that is an easier way to remember the order of Jacobian in terms of number of PQ buses and the PV buses. Okay. Now, if suppose we wish to calculate the correction vector, then we will have to take the inverse of Jacobian. Now, if Jacobian is a singular matrix, then its inverse would be 0. That means the correction vector cannot be determined and system is thus said to be unstable. If mod j is 0, system is unstable. Okay, whenever the determinant is 0. Okay, now let us take an example. It is saying a 100 bus power system network has bus 1 as the slack bus. Okay, then we are left with 99 buses, out of which 20 are PV buses. So PV are 20 and remaining are PQ. Then PQ will be how much? 100 minus 1 minus 20, that is 79. Now in the fifth iteration, Newton-Raphson flow PV buses reactive power limits are violated. So that means 5 PV buses need to be converted to 5 PQ. Then how many PV are left? 15. How many PQ are left? 79 plus 5, that is 84. We need to calculate the size of Jacobian submatrices. So J1 was n minus 1 cross n minus 1, that is 99 cross 99. In J2 the order was n minus 1 cross n minus m minus 1. So this will be 99 cross 84. J3 was del q by del delta, that is n minus m minus 1 cross n minus 1, and J4 was square matrix 84 cross 84. So this is the size of Jacobian submatrices. Now let us see what are the elements of the Jacobian submatrices. So the first submatrix is J1, which is equal to del P by del delta. Now equation of Pi as we derived earlier was J is equal to 0 to 1 to n mod Vi mod Vj mod Yij cos of delta j minus delta I plus theta ij. Now let me separate the ith term from here. J is equal to 1 to n. J is not equal to I mod Vi mod Vj mod Yij cos of delta I minus delta I plus theta ij. And if I is equal to j, then the term would be mod Vi square Yii, delta I and delta j will get cancelled out. Now if we calculate del Pi by del delta I, that is the diagonal elements of J1, then it will become, the derivative of first term would be sigma j is equal to 1 to n, j is not equal to I, derivative of cos is minus sign and minus sign will become plus sign, mod Vi mod Vj mod Yij sine of delta j minus delta I plus theta ij. Derivative of this term would be 0. So now if we wish to write it in a more compact form, this form resembles Qi. So I will write how much it will become, minus Qi and minus mod Vi square mod Yij sine theta ii. How I have written it is, I have added and subtracted this term so that this condition goes away. J is not equal to I. If you add this term, then this condition will go away and this will become minus Qi. So that is how we have arrived at the diagonal element. If we wish to derive the non-diagonal element, that is del Pi by del delta j, then this summation will go away because we are differentiating for a particular value of delta j. It will become mod Vi mod Vj mod Yij minus sine delta j minus delta I plus theta ij. So that will be the case when we are calculating the off diagonal element. Why summation goes away? Because we are calculating with respect to, let us say, delta 2, then derivative of the delta 3 term would be 0. Now let us calculate the elements of J2. Now J2 was del P by del mod V. Just now I write down the expression of P, sigma j is equal to 1 to n, j is not equal to I, mod Vi mod Vj mod Yij cos of delta j minus delta I plus theta ij plus mod of Vi square Yii cos of theta ii. Now if we calculate the diagonal elements, that is del P by del mod Vi, then this term would become sigma j is equal to 1 to n, j is not equal to I, mod Vj mod Yij cos of delta j minus delta I plus theta ij. Derivative of second term would be 2 mod Vi mod Yii cos theta ii. Now multiply and divide by mod Vi, or multiply both sides by mod Vi. So it will become j is equal to 1 to n, j is not equal to I, mod Vi mod Vj mod Yij cos of delta j minus delta I plus theta ij plus 2 mod Vi square mod Yii cos theta ii. Now this expression is same as P, just there is an additional term 2. So this can be written as Pi plus mod Vi square mod Yii cos theta ii. So that is how this can be written as a more compact type of form. Now if we wish to calculate the off diagonal element, because this is a matrix, so it will have diagonal as well as off diagonal elements. Then we will calculate del Pi by del mod Vj. So it will become, this summation will go away, mod Vi mod Yij cos of delta j minus delta I plus theta ij. Summation goes away because if you are differentiating with respect to V2, then the terms where V1, V3, V4 appears, the derivative will be 0. Okay. So if we multiply it by mod Vj both sides, it will become mod Vi mod Vj mod Yij cos of delta j minus delta I plus theta ij. Now let us calculate the elements of J3, which is equal to del Q by del delta. So let me write the equation of Q. J is equal to 1 to n. Let me separate the ith term, mod Vi mod Vj mod Yij sine of delta j minus delta I plus theta ij minus mod Vi square mod Yii sine of theta ii. Now if we wish to calculate diagonal element del Qi by del delta I. So this will be minus j is equal to 1 to n, j is not equal to I, then sine derivative will be cos, so it will become plus cos of delta j minus delta I plus theta ij. Then the derivative of this term would be 0. Now this term resembles power, but the j is not equal to I, so we will add the ith term and subtract the ith term. So that is mod Vi square mod Yii cos theta ii. We have added and subtracted this term, so it can be expressed in terms of Pi. Okay, so that is a more compact type of form. Now if we wish to calculate the off diagonal element, then del Qi by del delta j. So it will be, if we differentiate with respect to delta j, j is equal to 1 to n, j is not equal to I. Sorry, the summation will go away because we are differentiating with respect to delta j. And suppose if we are differentiating with respect to delta 1, it will appear in only one term. So it will be mod Vi mod Vj mod Yij cos of delta j minus delta I plus theta ij. I hope all of you are understanding why I am replacing the why I am removing the summation sign, because suppose if you are differentiating with respect to delta 1 or delta 2, then that term appears only one term inside the summation, so derivative of the other terms of the summation will be 0. But if you are differentiating with respect to delta I, it appears in each and every term. But this j is dependent on the index of j. Let me calculate the last element, that is j4, which is equal to del Q by del mod V. Just now I wrote the equation of Q minus summation j is equal to 1 to n, j is not equal to I, mod Vi mod Vj mod Yij sine of delta j minus delta I plus theta ij minus mod Vi square Yii sine of theta ii. Now if we want to find diagonal element del Q by del mod Vi, then it will be minus j is equal to 1 to n, j is not equal to I, mod Vj mod Vi Yij sine of delta j minus delta I plus theta ij minus 2 mod Vi Yii sine theta ii. Now this term appears like the initial term, but here one voltage is missing. So let me multiply both sides by mod Vi. So it will become mod Yij sine of delta j minus delta I plus theta ij minus 2 mod Vi square mod Yii sine of theta ii. So this is same as the initial term, just there is one additional term like this. So this can also be replaced as mod Vi into del q by del mod Vi. It will be actually Qi minus mod Vi square Yii sine theta ii. So that will be the diagonal elements of J4. Okay. Now the last is the off diagonal elements of J4. Then we will have to differentiate Q with respect to Vj. It will come out to be, summation will get removed, minus Vi Yij sine of delta j minus delta I plus theta ij. We will multiply both sides by mod Vj. It will become minus Vi Vj Yij sine of delta j minus delta I plus theta ij. Okay. So now what is the algorithm that we will use? First of all, we have calculated all the terms. So what we can write is delta P delta Q is actually, we can write like this, J1 J2 mod V, J3 J4 mod V. Why I am multiplying it by mod V? Because here I will take delta V by mod V. As you saw, the elements that we calculated del Q by del mod V, here also we took mod V and mod V into del P by del mod V. So that way the elements became compact, and hence we will use it something like this. Okay, this can also be written as HNJL. That is, we have given these matrices a name, that is H, N, J and L. Now let us see what are the steps to be followed when we are solving a problem using Newton-Raphson. So the step 1 remains the same in all the methods. We have to take Y bus matrix. Now if n is the number of buses and 2 up to m are PV buses, then m plus 1, m plus 2 up to n will be PQ buses and bus 1 will be slack. Here we will set iteration count as 0 and tolerance as 0.0001. Okay, so here only we will set the iteration count and tolerance. Now in step 2, we assume some values. So for PQ buses, we assume Vi is equal to 1 angle 0, that is for all I belonging to m plus 1 up to n. And for PV buses, we assume only delta I is equal to 0 for all I 2 up to m. Okay, so that means delta I assumed as 0 for PV as well as PQ buses, but mod Vi is taken as 1 only for the PQ buses. Now we will calculate Pi and Qi for all I is equal to, Pi can be calculated at all the buses PV as well as PQ. So Pi will be calculated for all I 2 up to n, but Qi can only be calculated at PQ buses. So I m plus 1 up to n. Okay, that is your Pi calculated. Now we will calculate the mismatch vector in the next step, that is delta P and delta Q. Delta P will be P supposed minus calculated, okay, delta Pi, and similarly delta Qi will be Qi supposed minus Qi calculated. So this delta Pi can be calculated for all buses 2 up to n. For PV as well as PQ, this can be calculated only for PQ buses, that is m plus 1 up to n. Okay, then we get a mismatch vector, that is delta P and delta Q. Now the next step should be finding the Jacobian. So here we find the matrix, that is the modified form of Jacobian H, N, J and L. We will determine this matrix in step number 5. In step number 6, what we will do is, we will determine the correction vector, that is delta mod V by mod V, which will be H, N, J, L inverse into delta P, delta Q. That way we will calculate the correction vector. Now we know that we have to update mod V only for PQ buses and mod delta for PV buses. So we will update delta for PV plus PQ buses, mod V only for PQ buses. Okay, then we again calculate Pi and Qi for all I 2, 3 up to n, and we check if generator Qi lies between Qgi min and Qgi max. If it does not lie within this limit, what we will do is, we will convert a PV bus to a PQ bus and then again repeat the initial steps. Okay, and if it still lies in this limit, then PV bus will be treated as PV bus for the future steps. So then what we will do is, we will again calculate delta Pi, that is Pi supposed minus calculated. So we again get the mismatch vector. Now we will check that if maximum of delta Pi is less than epsilon and maximum of delta Qi is less than epsilon, then the load flow solution converges. That is, there is no mismatch. If it is not if it does not occur, then what we will do is, we will go and repeat the entire process. So we will go on iterating until we get a condition where the maximum of the mismatch vector is less than epsilon. The next method is called as decoupled load flow method. As I told you, sensitivity of real power with respect to delta is high, whereas sensitivity of real power with respect to mod V is low. Similarly, sensitivity of Q with respect to delta is low. Sensitivity of Q with respect to mod V is high. So what we do is, we take del P by del mod V as 0, del Q by del delta as 0. So that means the off diagonal elements are reduced to be 0. So the Hn matrix will become now 0, L. So this way the solution becomes simpler and hence it becomes faster. That is why it is called as fast decoupled load flow method. Why decoupled? Because I have decoupled the equation of P and Q. Now P depends only on delta, Q depends only on on mod V. So let me compare all the methods. First method is Gauss-Seidel, Newton-Raphson and fast decoupled load flow. Now first is calculation. In Gauss-Seidel it is very easy. In Newton-Raphson it is difficult. In FDLF it is moderate because two matrices are eliminated. Now number of iteration, n. Here it will be more because each iteration is less time consuming but it has a slower convergence. In this it has least, it has moderate. Now time per iteration. Time per iteration is least, highest, moderate, because for each iteration we have to calculate the entire Jacobian. Then convergence, that is the rate at which you obtain the solution. It has a convergence of linear, that is values will fall on a straight line converging toward a certain value. It has quadratic, and it has geometric. Geometric means in the form of GP. And the last is accuracy. It has good accuracy. It has the best accuracy. And since it is based on assumptions, it has the least accuracy. It is the fastest but with the least accuracy. And remember, the Newton-Raphson method does not depend on choice of slack bus, whereas Gauss-Seidel method depends on the choice of slack bus. That is, in Gauss-Seidel you may or may not obtain the solution depending where you have chosen the slack bus. And the benefit with the Newton-Raphson, the biggest benefit that we get is, no matter what is the size of the system, number of iterations are almost the same. So let us see a problem based on size of Jacobian, which is most commonly asked in GATE. We have been given 300 buses. So n is 300, out of which 20 are generator. Okay. 25 are with reactive power support. So compensation are 25. Capacitor are 15. Other are load buses. So how many are load buses? 300 minus 60, that is 240. Now we need to perform the load flow analysis using Newton-Raphson. We need to find size of Jacobian. Now as I told you, slack bus is also a generator bus. So overall PV buses will be equal to 20 minus 1, that is 19, plus we will take the compensating buses as also PV buses. So it will be 44. PQ buses will be load buses plus shunt capacitor, that is 255. Now as I told you, size of Jacobian is PQ, 2 into PQ plus PV, 2 into 255 plus 44, that is 554. So size will be 554 cross 554. Okay, that is the size of Jacobian. Now let me summarize what we saw in this lecture. We saw Gauss-Seidel method, which had a better convergence as compared to Gauss method. Then we saw Newton-Raphson method, that it is used to solve the nonlinear algebraic equation. Here we saw three vectors: delta P delta Q mismatch vector, then Jacobian, del P by del delta, del P by del mod V, del Q by del delta, del Q by del mod V. And we saw the size of each Jacobian submatrix. It was n minus 1 cross n minus 1. Then it was n minus 1 cross n minus m minus 1. It was n minus m minus 1 cross n minus 1. It was n minus m minus 1 cross n minus m minus 1. Then we saw the algorithm for the load flow, and we saw the size of Jacobian was 2n minus m minus 2 cross 2n minus m minus 2. We calculated each of these matrices, and we also saw the fast decoupled load flow method, in which we assume that P is a function of delta and Q is a function of mod V. Okay, so this is all about your load flow analysis, and it forms the last unit of our power systems syllabus.